First of all, to everybody already assembled, thank you for coming. It's great to have your time, attention, ideas, etc. So thank you to everybody for attending. Really greatly appreciated. And then to Vlatko, I was just thinking about his job title, Professor of Quantum Information Science at the University of Oxford. A little bit of envy from me there straight away. That's a cool job title.
Yes, I
Um,
think they
but
allowed me to choose it myself, I think, ultimately, which, yeah, yeah,
that's cool, yeah.
yeah.
And even more than that, he plays guitar, so
Occasionally, not as much as I would like to.
yeah. So I read your book a few months back. I read it straight through. This is your first book, I
Yes,
think, or
yes, yes,
there's a new one out now, which we will
yes.
possibly talk about as well. Your book, I read it, very readable, very erudite. It really has made me think, and I mean that present tense. I'm still thinking, and that's a truly a sign of an important book, I think, when it's
Thank you.
living with you. So thank you very much for attending today. Thank you to everybody else for attending. I'm going to hand over straight to you, Vlatko. Richard will
Thank you.
organize the session at the end, and I must just credit Richard with setting this whole session up. So Richard will take over after you've spoken, Vlatko. But over to you, and thank you so much.
Thanks very much. I'm very grateful to be invited, Peter, and it seems to me that we have many things in common. Um, uh, Certainly, so what I try to choose now is a set of slides that I hope would be of interest to you. I must admit, I don't know much about cybernetics. Of course, the pioneering book by Wiener is there, which I think anyone who works in this field has read, and there are many other books I think which are fascinating. And it seems to me that it's still a topic that's extremely exciting to explore, especially within the context of quantum mechanics and possibly even going beyond. So it's in this spirit that I will say a few words. And like I said, I'm very happy to engage in any discussions. Please ask me questions even during my presentation if anything is unclear. Um,
Thank you.
as you mentioned in my book, Decoding Reality, I think this came after my PhD, probably 10 years beyond, maybe even 15 years. And during my PhD, I applied Shannon's information theory to entanglement. And I thought that was the best way to quantify entanglement. At that time, I think people were starting to do very basic experiments only with a handful of particles. So you would have maybe two entangled photons or two entangled electrons or two entangled atoms at best. And then people would test various quantum properties. And I felt that the transformations, what's possible to do with entanglement, how much you can enhance communications, computation, was actually best quantified with measures that Shannon already introduced. I think they have to be adapted to quantum mechanics, of course, because we use a different mathematics in quantum mechanics to classical physics. But even with this kind of quantization, you are effectively more or less using the same concept of Shannon entropy, mutual information to quantify correlations, and so on. And I think as I was doing my PhD, just you tend to read around, of course, and um, what really fascinated me and impressed me is the usage of Shannon's ideas, and ultimately that ended up being the book Decoding Reality. Um, Now, for a physicist, of course, you'd like this kind of new idea to also do some useful work for you. I think we're very pragmatic in a way that all of these questions are fascinating for anyone, obviously, and as a philosopher, you may contemplate them even without worrying whether you will ever be able to apply them. But of course, in physics, we'd like these new ideas to really give us something new, and that's the spirit of this presentation. So somehow I thought it would be interesting to maybe reverse the arrow and play around a little bit with this notion of information possibly being more fundamental than what we think of are the constituents of everything, matter and energy, and of course the exchanges between the two. So that's what physics is really all about. And I thought it would be interesting to see whether that's a bit like what John Wheeler suggested, it from bit, that really the its of physics come from bits of information. Um, but what's also interesting, and I think you mentioned it in your email as well, that you can go the other way, and quite a lot of my field is based on the opposite direction to Wheeler. So it's not it from bit, but somehow bit, or in this case maybe quantum bit, qubit from it. So this is this old question: what comes first, in some sense? And as I said. What's fascinating to many people, actually, to many of my colleagues, is that it seems to us that the rules of quantum mechanics are incredibly close, even the way they are phrased, to some form of information, which was the intuition that I followed, really. Um, and um, and of course, classical information gives you a certain amount of power in terms of communications, or cryptography in terms of computation, and then quantum mechanics enlarges this set of possibilities. Um, and again, for a physicist, it's natural to think that every time we discover new physics, presumably we could be using these new systems and our new understanding to encode information in yet another way. So if there were to be a new revolution in physics, and actually that's what I'm exploring in the new book, then it seems to me that ultimately, of course, this will lead to novel kind of computation, but possibly even more than that, and that's something I will say later. So why am I saying that physics in some sense can be thought of as being about information? I mentioned quantum mechanics, and I think quantum mechanics comes much closer than classical physics to this. But even classical physics, I think we discussed a lot about determinism, being able to make predictions about any observation that we are going to make in the future. And here the concept of information is crucial. And you really need to know how much information you have, and you need to understand the speed of processing this information. So physics is full. I'm writing this in a kind of very informal way, but physics is full of these kind of demons, which are the entities that possess basically the ultimate information. In this case, I'm talking about classical demons, and I think the famous one is, or two famous ones are due to Laplace and Maxwell. And Laplace's one is of course all about determinism. So Laplace noticed that if you knew the positions and velocities of all the particles in the universe at any instant in time, then you would automatically know the rest, all the future times and even all the past times. You can even take the present, or you can take the beginning of the universe. It doesn't really matter. But Newton's equations are fully deterministic. And it's the same kind of determinism that Maxwell is talking about. But Maxwell is worried about a law that seems to be profoundly statistical in nature, which is the second law of thermodynamics. The fact that the entropy of a closed system, if you take the whole universe as an example, if it is a closed system, then the entropy should never decrease. It tends to its maximum, and then it stays there once it equilibrates. And Marx was really worried that if there was an entity, if you had a demon that really could access all the relevant data for all the, let's say, molecules in a gas, then this entity could actually reverse all the velocities, for instance, and bring the gas back from the future position back to any past position. And this seems to be apparently contradicting the second law of thermodynamics, because if you believe that the entropy was increasing in the forward direction, then if the demon manages to undo and reverse everything, it must be decreasing in the backward direction. In fact, this was one of the objections against Boltzmann's approach to the second law of thermodynamics as well. How can you claim that entropy at all increases under any circumstances if the underlying laws of physics are reversible? And it's something I want to touch on a little bit later as well. But physics, we think a lot about what does it mean? What kind of information, first of all, is necessary and sufficient in this case? And then if you had that information, what would happen, or would there be anything else that could limit you from accessing that? Now, quantum mechanics really amplifies this. The way that Schrödinger talks in one of the pioneering papers about states of physical systems, he literally calls them catalogs of information. So that's interesting. It really does take. Obviously, this was before Shannon and before this was done formally in an axiomatic fashion. But what Schrödinger is saying actually is that when you write down states of your system, what you're really writing down are probabilities. In quantum mechanics, you're doing amplitudes, you're doing the square roots of probabilities. You have to take the absolute modulus square of these entities to get the probabilities. But effectively, what your state of the system does, it lists all possible tests, as it were, that you could perform on your system. And for each of these, at a given time, you assign various probabilities. So it really is like a betting portfolio. I think that's what prompted me to write a section on betting in my Decoding Reality, because I realized that actually the logic is very similar, of course. And and then the laws of physics, if you want to continue in this fashion of information theory, if you're a quantitative analyst, right? What you'd be saying is actually, if I wasn't betting now, but if I were to bet in 3 hours' time, how would I have to update the probabilities in my portfolio? How would I have to change them? And actually, you can think of the laws of physics as doing exactly this for you. So they're somehow giving you a dynamical translation in time, which contains, providing, of course, you understand the relevant information about your system. In this case, would be the energy operator. It would be the Hamiltonian in quantum mechanics. And if you knew your Hamiltonian, you could simply evolve your state and you could update it at any time in the future. And incidentally, in this sense, this aspect of quantum mechanics is as deterministic as anything in classical mechanics. So it's a very interesting question. Where does randomness come in? And that's something I want to mention now. So we use this. So basically, here I have this picture of a coin, and I'm using this very fanciful vector notation that in quantum mechanics we use extensively for states of our system. So it's a bit like what Schrödinger would say: if you have two states, if you have heads or tails, and you are trying to predict as you toss this coin what the outcome would be. These two entries inside these vectors, basically the upper and the lower entry of the vector, would simply contain the probabilities for these two outcomes. Or in quantum mechanics, again, these would be the square roots of probabilities. They would be complex numbers in general. But so one extreme would be the heads of your system, and I'm labeling it as one vector, and the tails, and so on. And what's interesting in quantum mechanics, and that's the key difference, is this concept of a superposition of different states. So in quantum mechanics, as soon as you know that you have two possible states of your system, quantum physics suggests that you can actually ultimately prepare any superposition of these two. And that's something that doesn't exist classically. And I want to go through that. Classically, what does exist, of course, is an uncertainty that you have, a bit like tossing a coin. It's an uncertainty, but I think in classical physics, you would attribute this uncertainty to your own lack of knowledge. If you knew how the coin was tossed, exactly with what's initial speed, from what angle, what position, you could actually use Newton's laws to deterministically tell whether it's going to come up heads or tails. So all uncertainty in classical mechanics is superficial, so to speak, not fundamental. It's superficial in the sense that you could, in principle, make it less uncertain, and it's really only up to you and the accuracy of your measurements, or the ability to store the information, or whatever else is limiting you there, time, money, all of that stuff. But it's not really to do with the system itself. The system ought to behave fully deterministically. And now we have a quantum equivalent of tossing a coin. And it's the basic, this experiment, I think if you open Feynman's lectures on quantum mechanics, he will say this contains all the mystery of quantum mechanics. And it's true. All experiments that we do are simply just more intricate versions of an interference experiment that I will describe now. And so here is the interesting behavior. If you send here I'm always thinking of photons, because these are the most convenient particles to use to do this experiment. But they've been done with material objects. People have done this experiment with objects that have hundreds of thousands of atomic units. So they are basically few orders of magnitude away from a living system. So, if you ask me how far we've got to in physics, it's become pretty macroscopic in many ways. And we do know that all of these effects persist up to that point. Of course, there may well be a boundary at some level. In my new book, I'm arguing against it. Actually, I'm arguing that we will get a lot more mileage by thinking about everything in a quantum mechanical way. But certainly at this level, this is true. So you send a single photon through a piece of glass, a beam splitter, which actually has the property that it has a certain probability to reflect a photon and a certain probability to transmit a photon. And this is the key property number one that Einstein, you will probably know about it. Einstein complained a great deal about this, and this is the origin of I don't think God plays dice with the universe. But it seems, and in fact, this was one of the first applications of quantum technologies for random number generators. It seems to us that there is no algorithm, that there is certainly no formula within quantum mechanics that would tell you each time you execute this experiment and you send a photon at the beam splitter, we have no way of deterministically predicting which detector will click at any given time. Of course, what quantum mechanics does allow is that if you do an ensemble if you keep repeating the same measurement, you prepare exactly the same photon in the same state, you fire it the same way, the beam splitter stands the same way, the detectors are there, you make sure all the conditions are the same, what you can get is the statistics over many trials. And if the beam splitter is 50-50, it really means that in the long run, half of the photons would end up in detector one and the other half in detector two. So it really does behave like a coin. It's like tossing a coin. But with this extra understanding that there isn't a way, unlike in Newtonian mechanics, where if you really told me how you initially toss this coin, I could, in principle, it may be difficult computational, but I could, in principle, calculate. I would have to know probably the air and properties and all sorts of other things. But yes, I could do it. But here, there is nothing that does that for us. And the thing that actually tells us that this is the case is the part B of this experiment. And that's the key. That's the kind of the central mystery, as Feynman would say. So if you didn't detect the photon, if you remove the two detectors, but you put two mirrors instead, then suddenly you recombine the two possibilities and you put another beam splitter. So this is the mysterious thing. I spent about few minutes now convincing you that the beam splitter is the most random thing you can imagine in the universe. And now I add another beam splitter. And the intuition would suggest that two random things in a row have got to be at least as random as each of these. I mean, all I can do is generate even more randomness. So if I ask you what happens now after the second beam splitter, which of the detectors clicks, the answer should be, well, what's the difference? It's like tossing a coin twice. I mean, what difference does it? It's still going to be random heads and tails. But actually, in quantum mechanics, it becomes 100% deterministic. And what happens in this experiment is that the detector 2 never fires. If you did this appropriately, if you made sure that the path lengths that the photon covers in both cases are equal to one another, then every time you fire a photon, only detector 2 will click. Now it's suddenly coming out deterministically out of one single port of the second beam splitter. And people have tried, and there's zillion of different interpretations of quantum mechanics. Again, I have my own view, and I think I talk about it a lot, and I don't want to bore you with all of these details. But the only way we can account for this, and I think the language somehow must reflect this, is to acknowledge that after the first beam splitter, the photon really goes both ways at the same time. So we have to acknowledge that the photon does have wave properties. It's not just a particle that gives you a click when you detect it, as would an atom or an electron or a subatomic part, anything else. Here, the photon, and it's true for all other particles that we tested, suddenly behaves like a wave, and it goes in both directions after the first beam splitter. And what happens at the second beam splitter is exactly what happens with waves, that as they are coming out in one direction, they are fully in sync, these two waves. The peaks of one wave coincide with the peaks of the other wave. Whereas in the other case, the two waves are exactly out of sync by the right phase that the sum of them cancels out completely. So the maximum of the first wave is exactly at the point where the minimum of the second wave occurs. So when you sum them up, and these are these amplitudes in quantum mechanics, when you sum them up, they completely give you a zero probability for the detector 2. That's the way we do our mathematics. And like I said, the best way, and no one has come up with any other way of talking about this, the best way is really to acknowledge that the photon splits and takes both of the parts at the same time after the first beams. And then these two parts merge together and they enhance each other in one particular direction and they cancel out in others. And so that's the interesting thing in quantum mechanics, that if you combine your seemingly individually random components, but if you put them together in an appropriate way, you can really get something deterministic. And again, I mentioned that you can quantify this using Shannon's concept and so on, and I don't want to talk too much about it. What I want to do is immediately tell you about quantum computers from here because um, once you acknowledge that a photon exists in two different arms of the interferometer at the same time, what you can do, and people do this routinely, is you can perform one kind of operation in one arm and a different kind of operation. You can put a piece of glass of a certain thickness in one arm and another piece of glass of a different thickness in the other arm. And what this tells you, if you think of this as a form of computation, is that each of these paths that the photon takes could, in principle, perform a different computation. And that's basically ultimately leads you to the exponential advantage that you get in some applications of quantum computers, not all applications. And that's also a mystery. Which problems exactly lead to a definitively large speed up, and which other problems are actually as difficult as classical. Quantum computers can't help us. They're as slow as the computers that we have now. So I'm here just extrapolating, and I'm saying, imagine that after the first beam splitter, I don't combine the two arms of the interferometer, but I introduce two more beam splitters. So each of these paths I split even more. So I'm generating now more and more quantum bits. They're all sitting in a superposition. So if I did this with 3 bits, if you like, as I have here, you would actually in quantum mechanics have 8 different possible states, and they would all exist at the same time in a superposition. So in fact, rather than feeding in one number at a time into your classical computer and getting one output corresponding to that number, whatever you did in your computation, let's say you took the cube power of your input number, now you could in fact feed in a superposition of quantum bits and evaluate your program, whatever it is that you are running, on each of these uh, numbers individually, and it would come out as one big superposed state with functions of these numbers as the outputs. And that's basically what your quantum computer does. So that was a realization that I think occurred to Feynman, not formally in terms of computation. I think he was thinking more in terms of simulating physical systems. And the point he was making is that surely if you want to understand quantum systems, you should use quantum systems to simulate quantum systems. It's much more effective than if you use classical systems. Suddenly, to simulate n quantum bits, you would need 2 to the power of n classical states, and you would need to really process them simultaneously to account for all of this. So you can see that it gets out of hand exponentially quickly. And then it was really David Deutsch, my colleague at Oxford, who formalized this and gave both the quantum Turing machine. He quantized the Turing classical computer and the circuit model, and showed that these two are equivalent ways of talking about quantum computation. And this, as you know, is a very active field. There is still, of course, a question whether we will be able to build a large-scale quantum computer. So people who now do these things talk about up to 100 quantum bits. Various companies are now announcing thousands of quantum bits, but they're not really fully quantum. I don't think these are universal computers that could do any computation. They can do some quantum operations, but they are very limited. So I think if you really want to talk about universality, we're still limited to no more than 100, maybe even fewer than 100 quantum bits. Again, someone like me, my bias is that really it is a question of time and the investment. I don't think that there is a fundamental obstacle in physics that prevents us from doing this. But so this is one of these images beryllium ions glowing as you kind of shine some light. They're trapped. This is, of course, slowed down many times. These are frequencies that are megahertz. So they're basically million times faster than the image that we are looking at. And obviously, it's been amplified greatly so that we can see them. But this is an old experiment. I think this was already done in the late 90s, and it's just incredible that um, we went from early 1900s when people doubted still the existence of atoms. Boltzmann had lots of problems arguing against people like Mach and various other doubters of the reality of atoms. And within a span of less than 100 years, we actually can now see them. We can shine laser light on one of them and excite a specific one and not touch any other atoms. So people can do all sorts of fancy things. And there is a number of Nobel prizes now behind this kind of technology. So it seems to me that ultimately we will be able to make quantum computers, and this really um, is possibly a vindication of this thing that the laws of physics, in this case, the laws of quantum mechanics, do tell us, they do dictate what kind of computations we can do, how much power we can get out of our computations or our communications or anything else. And now maybe what I would like to do in this last bit is mention something that I find very interesting, in fact, but it's much more speculative. And the reason why I wrote and beyond in my slide is really to tell you about it. This is just the last slide on this bit, which tells you about how you can encode. Of course, I already mentioned the beam splitter that can encode zeros and ones as different outputs of your beam splitter. But of course, you can use states of matter, you can use an atom, you can use an electron, which is sitting in an orbital close to the nucleus, and in another one, which is a little bit further away from the nucleus. And you can treat this as your logical zeros and ones. And then if you shine appropriate color laser light onto this electron for a specific amount of time, the electron will move from the close orbital to the further orbital, which is your bit flip, if you like. It's flipping from the state 0 to the state 1. If you do this for half the time with exactly the same laser frequency, you would have prepared a superposition of the electron being close to the nucleus and further away simultaneously. And my colleague, David Lucas at Oxford, can do this with the highest efficiency in the world. I think with 8 nines probability, he can move an electron from A to B. 8 nines meaning 99.69 probability, certainty that you will end up in the desired final state. So to me, again, speaking as a theoretical physicist, I'm always amazed at technological progress and what people can do, and that's why it gives me confidence that I think probably making a large-scale quantum computer is just a question of it's an engineering question, really, how to control all the errors that exist, and we can talk about that if anyone is interested. I'm happy to elaborate on that. But now, what I want to mention is the aspect that I think my colleagues David Deutsch and Chiara Maletto are extremely fond of. And in fact, it does tell you that this is probably an unfinished revolution, as I'm trying to dramatize it in this slide. So the question is really, should we go beyond the framework of computers in order to really capture everything out there in the universe? And I think many people would say yes. Of course, this is a very speculative topic, and probably there are as many opinions about this as there are people out there, and it's a bit like the interpretations of quantum mechanics. But what David suggested a little while back is that instead of thinking about universal computers, we should actually follow von Neumann. And I think this really goes in the direction of cybernetics much more. And we should talk about universal constructors. And universal constructors are presumably, again, we don't understand this very well, but they're presumably entities that would have a larger set of, larger repertoire, larger set of things they could do than the computers that we actually have to routinely program. So that's the idea. And I think here, of course, there is this obvious example that computers cannot really reproduce themselves. And it's precisely why von Neumann, who incidentally in that paper or in a sequence of papers, I think he was really thinking about colonizing Mars. And he thought, how do we send out robots there to set things up for us? How do we make sure that these robots after some time they will degenerate, wear and tear, and things like that. How do we make sure that they are able to, by themselves, first of all, find faults within themselves, and then find material in their neighborhood that would help them repair these faults so that they could last as long as it's needed. And in fact, von Neumann shows that classical error correction, if your if the errors of your individual steps in your computations are small enough, and by the way, it's the same story in quantum fault tolerant, it's exactly the same logic as von Neumann's. If your error is sufficiently small, then you can actually encode your information through redundancy. Instead of using a single bit, you use a number of bits to encode the same bit value. But if you use sufficiently many of them, then you can push your error rate to any desired um, approximation that you like. First order, second order, if you encode it again and concatenate and so on. So actually, von Neumann was really thinking about mimicking, upgrading, so to speak, computers so that they become more like living systems. And I think that's one of the visions here is that if we instead of just looking at quantum computers, think about quantum constructors, and these would be defined as entities, as machines that could in principle execute any physical transformation that's possible to execute. You can see why this is intimately connected with the laws of physics. Um, and somehow, if you unify physics and constructors, then this vision, and that's the last thing I'm saying on this slide, should possibly then also cover living systems, which I think is exactly what cybernetics and I guess the beginning of cybernetics was all about, to capture things that living systems can do and ultimately maybe even consciousness thinking. And of course, we don't have the reason why I keep saying it's very speculative, and I can tell you a few things and I will stop there, but we don't have, and it's even questionable whether you can have a set of axioms that define a constructor in the same way that um, Turing defined a universal computer. Universal computers are extremely easy to define. As you know, all you need is a tape. You need a head that can scan these tapes and erase bits and write new bits in, move left and right, and that's it. Basically, you can show that anything that can be computed really can be computed by this machine. And the same is true for quantum computers. Don't really change this aspect. What they do change is the speed at which you can do this. But now the question is, if we upgraded this to an even more powerful entity, Some people call them like, 3D printers would go in that direction. So, entities that can also make things for you rather than just compute things for you. Um, Now, what's interesting here, and again, that's interesting to me as a physicist, and that's maybe the thing I will say, and then I can conclude. What's interesting here to explore is that the vision is to move away from the dynamical formulation of physics, which is what I was using in the first part of the talk. So, as I said, what we do in physics, we write the initial state of the system down. And then we have this magical function called a Hamiltonian, which tells us how this state changes, how does it evolve in time. And that's all there is to it. So all the problems in that sense are pushed, um, simply confined to knowing your initial state and knowing the Hamiltonian of your system. And very much echoing Laplace in this sense. Of course, what you cannot predict in quantum mechanics is what I was presenting, that if you have a superposed state of your system, and if you were to measure to see which of the states, which of the output ports of the beam splitter your photon is in, then quantum mechanics actually says all you can do is attribute a probability to this. And all you can do is verify this probability in an ensemble of measurements, but each single measurement is completely random. There is no algorithm for that. Um, However, what constructors would do for us, they would try to make the rest of physics a little bit like, that's again what comes to mind to a physicist. The first thing that comes to mind is a bit like thermodynamics. So thermodynamics is underpinned not by dynamical principles, but it's underpinned by two or three or four laws, as many as you think you need. But the first law is energy conservation. It says whatever you do, whatever transformation you make energy, the total energy will always stay the same. And the second one is this famous entropy increase law, that whatever you do in a closed system, you can never decrease the entropy of your system. And these are two very general principles. They are nothing to do with the states of your systems. They're really all to do with what's possible and what's not possible. And of course, this goes back to the Victorian times, the Industrial Revolution, and the famous experiments that were done then, where people like James Joule noticed that if you have this beer he was a brewer, Mancunian brewer, as you know, and I think he noticed that if you have beer confined in a barrel and you steer it, then you can get it to increase in temperature. But nothing you can do of that mechanical type without obviously cooling it down. But if it's really fully isolated, there is no transformation that you can implement on this to reduce the temperature of the system. So in terms of second law, you can always increase the entropy of your system. You can increase the disorder in a closed system, but nothing you can do. There isn't a constructor, if you like, that can actually execute the reduction in entropy inside the closed system. And the question that I find, so first of all, the first interesting point here is that again you are using this very beautiful interplay between physics and computation, or information, or constructors in this case, possibly cybernetics, where you could go in two different directions. You can say, if we were to upgrade constructors from classical to quantum, how much more powerful would they be? That's kind of going from physics towards computation. But you can also go the other way around, which I think is what David was suggesting, and asking what would happen if the whole of physics was actually phrased in terms of these constructors. If I just simply list for you all the things that can be done in this universe, is that enough? Is there a different way, an equivalent way of capturing our fundamental laws? So this is an approach that's more like principle driven, a bit like Einstein's special and general theory of relativity. And I think Einstein himself was um, very much fond of thermodynamics and the way that these very general principles lead you to some very profound conclusions. So, so that's it. And I don't want to, there is a formal way of talking about these constructors, and we can get into that. One interesting thing that I want to point out, and then I will show you this final idea that I think is fascinating in this direction, what could happen. But what's interesting is that if you engage in this kind of thinking about possible and impossible tasks, you could actually explain how irreversibility, and this is one of those big questions that I mentioned already when I mentioned Boltzmann, how can you have anything irreversible if all of our fundamental laws are time reversal symmetric, which means that any transformation that takes place in the forward direction can actually, according to physics, also, and it's equally valid, go backwards. In fact, it's as simple as putting a minus sign in front of your time or a minus sign in front of your Hamiltonian, by the way, that we talked about. This will give you exactly the reversal of what you did. So the question is, why do we see things in the macro domain happening really only in one direction? Um, and is it really which property is now fundamental? The irreversibility as people who adhere to the fundamental nature of the second law, or is it really our underlying reversible dynamics? And there is a lot of discussion about this. But what is interesting is that in this case, you can, and this is maybe the slide that summarizes it, you can phrase it in a way that you can have it both in a sense. You can have the underlying reversible laws, but you could actually still show that there is no constructor that can faithfully implement it in the backward direction. So this is exactly a generalization of what I mentioned about James Joule and the experiments of trying to reduce the disorder of a closed system. So in terms of constructors, you would realize that there is a constructor which can execute a transformation from the state X to the state Y. However, if you want the transpose of that from the state Y to the state X, you can actually show that there is no such entity that can execute this transformation. So this is perfectly consistent with the fact that the underlying laws of physics might well be reversible. Of course, even this is an open problem in physics. You can, as you know, never say anything definitively, and you could prove yourself wrong next time you do an experiment. Now, the final thing I really would like to say, and that's what I find fascinating. Again, like I said, I'm a physicist, and I'm always thinking, um, whenever I see an exciting idea, I'm thinking, can this do really something um, useful for me in the sense of, can I conclude something new out of that? Is it going to lead me? Will this insight lead me to the new laws of physics? Is it going to suggest to me the kinds of experiments I should be performing in order to really to test any of this? And so I'm offering, this is extremely speculative, and admittedly I don't know what to do with it, but it's the closest I could come to it, which is to mimic one of the formulations of the second law. So Kara Theodori, a German mathematician, formulated in 1908 or 9, I think, quite early on. His friend was Max Born, the physicist Max Born, one of the pioneers of quantum mechanics. And Max Born complained to Kara Theodori that thermodynamics is not as rigorous as the rest of physics. He thought that it was a bit fluffy. He thought it was woolly and it needs to be tightened up. And who better to talk to than a formal mathematician in this case? And of course, Kara Theodori writes a paper about it, where his formulation of the second law is the one I wrote down. And it says, in the vicinity of every physical state, there are states which cannot be accessed adiabatic. Adiabatic is exactly what James Joule was doing. Isolated system that cannot exchange heat with the environment. Of course, if the system can exchange heat, you can always cool it down. You can put it inside the fridge and there's no problem. But if you prohibit the system from exchanging heat, then all you can do internally is increase the disorder and energy. And that's exactly what Kara Theodori says. And in fact, it's really powerful that a simple axiom like this can lead you to derive the entropy with all its physical properties that are relevant to us and so on. So this is yet another formulation in addition to Clausius and Kelvin, the two well-known ones. There is a Kara Theodori one, which is a bit more mathematical. But I thought, wouldn't it be nice to generalize this to the rest of physics? And that's kind of my final thought, which would be something like the second law of constructors. So how do we get these constructors to tell us about new physics? And I thought that maybe one of these we could really paraphrase the thermodynamical second law of Kara Theodori and say that in the vicinity of every possible task. So I'm trying to define the ultimate laws of physics as so tight. They're so, it's a bit like Einstein said, I want to know the thoughts of God and the fact that God had no other choice but to do exactly this with the universe. That would be the ultimate understanding. And here I'm kind of saying it in a way that in the vicinity of every possible physical task, there is immediately an impossible one. So the ultimate law of physics is so tight that if you tweak it even a little bit, you're going to end up with something that cannot be the case. How do you know that it cannot be the case is, of course, a different question. You need sets of principles, then, of course, that limit you to understand what's possible and what's not possible. So somehow I'm thinking in this way whether this could be the ultimate selector for the laws of physics and whether this would ultimately really be um, um, the way to think about physics, which would be much easier then to apply to the macroscopic systems, go into chemistry, and even more importantly, into biology, because of course, we are not sure if the laws of physics as they stand are sufficient even to understand life. So we are much more confident that chemistry probably we can account for by quantum mechanics. Even if we cannot compute all the bits, I think most people would be confident that quantum mechanics suffices. But I think once you make the next jump to living systems, then I think all bets are off. We really do not understand that. And the idea here is really to even phrase physics in a friendlier way to biology and really see whether this could do something for us. Thank you for your attention. I will stop here.
Wonderful. Thank you so much, Vlatko. I think we're going to Richard next, but that was wonderful. Thank you so much.
Thank you.
Yes, thank you, Vlatko. So, are you okay to continue? You've been talking for a while.
Of course, of course.
Yes, thank you. So, we do have a number of questions in the chat, but if people want to continue posting questions, please do so as we continue. So, I have a list of questions from the chat. If I could just first of all bring the page up and then bring people in. So Matt Day, you posted a number of really interesting points. The question I had goes right back to the beginning around the uncertainty principle and Laplace's demon. Would you like to expand on that at all, please, Matt? Oh, he's got a difficulty with his mic. No problems.
Yeah.
James Bryant, great question around localized information or knowing knowledge of the information in the universe. Where are the boundaries of information required, and how do we know? James, could I bring you in on that one, please?
Sure. Yeah. I mean, just going back to your coin toss and being able to predict the outcome. I know it's a long way back, but what level of information is required to predict it? Because if it's all the information in the universe, then presumably it's one, difficult, and two, definitely probabilistic. If it's local conditions, then I would suppose that it's not perfectly probabilistic because it's reliant on the context. So that was the basis of my question. So.
Yes, I think it's a great point. In fact, many of these discussions feature in arguments that Boltzmann had with various people. And I think there is there is this famous exchange with Loschmidt, which I think reminds me exactly of your point. How much information would we really have to know, and how far? What is the total volume, if you like, that I would have to include? A quick answer would say, well, certainly anything that could affect your system. If you imagine that nothing travels faster than the speed of light, then you would have to take, let's say, a sphere of the radius how long light would travel during your experiment, and this, of course, could be very big. So Loschmidt, when Boltzmann claimed that he could take a gas of molecules and prove that the entropy increases, Loschmidt said to him, how can that be when I could take that final state, reverse the velocity of each of your molecules, and they would then transverse exactly the reverse trajectories and go back to the original state. So now I just showed you that you can also decrease entropy. Apparently, Boltzmann replied on a single postcard, go ahead and reverse them. And I think this simply says what you are saying. Yes, maybe the dynamics tells us that in principle, this is fully deterministic, but in practice, in most of these cases, you're never going to have the full information. I suspect a coin toss is accessible. I don't think this requires that much information. But if you make your system, if your gas is big enough, even something as simple as that will very quickly become unpredictable. I agree.
Thank you.
Yes.
Great stuff. Hopefully, Matt. Yes, microphone fixed. Matt, would you like to come in, please?
Hello. Can you hear me?
Yes.
We can indeed.
Okay. Well, thank you for the great presentation. Lots of stuff to unpack. So, yeah, I did mention at the start, due to the Heisenberg's uncertainty principle, technically the Laplace demon should be impossible because you can't know the momentum and the position for even one particle, much less all particles.
Yes.
As for the Maxwell's demon, I think you would have I think you'd greatly benefit from looking at the work of Heinz von Forster. Because
Oh, I love that guy. I have his book actually. I think he's fantastic. He's a bit crazy. I'm going to use strong words there. I think a bit, he runs wild with some of the creative ideas, but I love them. I just love reading about this stuff.
yeah, he had a really good thought experiment for the Maxwell demon of reducing entropy. So you're getting order from disorder, which was
Yes.
like a box filled with cubes. And initially the cubes are all disorganized, but all you have to do is keep shaking the box.
Yes.
And
Yes.
eventually the cubes start stacking up on top of each other.
Yes. Yes.
So I think that's a really interesting thought
Yes,
experiment.
spontaneous organization, right? So these are all kind of ideas and models that ultimately try to explain living systems, right? Because that's the ultimate question. How come these you can call them Maxwell's demons, right? How do they spontaneously arise? Entities that are somehow trying to survive by reducing the entropy of themselves, right? And maybe the neighborhood as well.
Yes, and
Yeah.
I know he was a physicist as well, so he probably speaks some of the same language as
I
we.
guess so. I guess so. You're right. Yeah. Yeah.
Um,
Thank you.
Also there
Yes.
was another character. I can't remember. I can't really say his name properly,
Ah,
but Prigoni, I think. Ilya
Prigozhin.
Prigogine.
Yeah.
Prigogine.
Yeah. I think yes. Yes. Again, lots of his ideas mix in. Yes, I disagree. I'm familiar with what I think he's been or he was saying, but he um, I disagree with his views on quantum mechanics. I have I have a view in which I have a view of the universe in which there isn't any classical domain. Classical physics only arises approximately in some limit. And so it may become harder and harder to uncover quantum features as the system becomes more complex, more macroscopic, or whatever measure you have there. However, it is always quantum mechanical through and through. I think that's the only consistent way to understand quantum physics and avoid, by the way, any of the I should say apparent paradoxes that people claim are out there. So non-locality, I think there isn't
Yeah.
any non-locality, things like that. So Prigozhin had a very statistical mechanics view driven of quantum. So I think quantum mechanics is not statistical mechanics. It's beyond the quantum uncertainty is not a lack of knowledge. That's what I'm trying to say. It's not in your head.
Yeah.
It really is like that in the
It's like a
universe.
seesaw.
Yes. Yes. So, but that's besides the point. I think he did a huge amount of work in non-equilibrium thermodynamics, and that work in the
Yeah.
40s is very important. Yes.
And I'll just go back to von Forster as well and cybernetics specifically. So
Yes.
I think second order cybernetics is where it would really help with quantum mechanics because the observer effect and the whole idea of second order cybernetics is putting the observer in the system.
Yes.
And it's quite hard to wrap your head around. You have to go a bit into Maturana's autopoiesis, which is mainly biology domain,
Yes.
and it's having a self-referential loop
Yes.
to close it and become a closed system.
Yes.
But yeah, I think the observer.
If you're interested in the new book, okay, I've got advanced
Yeah,
copies. I don't know if you can see it, but
portals to
Yeah,
a new reality.
that's it. The new book is exactly an argument. Um, so it starts by arguing that observers must be quantized too. The only way to understand this consistently is that there is nothing intrinsically special about observers, special in the sense that they are not classicalizing anything. They are not there to get anything definitive, if you see what I mean. They're simply just another physical system. And
Yeah,
maybe I go through an experiment in this book that sounds like what you would like to explore, because you're talking about observer looking at the system and then even maybe communicating with another observer. So I think it's a beautiful question, and certainly I think I've only begun to explore this.
yeah.
And needless to say, experimentally, these are extremely difficult things. No one has ever been able to entangle even a living system with a quantum. Those are some of the experiments that I'm trying to do are actually to entangle two living systems, to entangle them in a quantum mechanical way. But I think we're really very far away from observers like ourselves.
I just want to go back quickly to Wheeler and Do you know of his delayed choice quantum eraser
Of course.
experiment?
Yeah, this is bread and butter for a quantum physicist. Yeah.
Yeah, I'm not a I'm a computer scientist, so I'm a bit in a deep end, not fully understanding it.
Yes.
But I
Yes.
think this is much in line with the observer effect and
Yes.
the it from bit.
Yes, but that's why I think my book goes against all of these. The prevailing interpretation is called the Copenhagen interpretation, and Wheeler was a supporter of Copenhagen.
So what's
The
that
the
like?
the thesis, I'll tell you in a second, but the thesis of my book is that this is why we have been stuck actually without a new breakthrough in physics with a new theory. So that's exactly what my book is arguing for. To go beyond that, and I think it will help to change so Copenhagen view says that whatever you think is quantum, in order to understand it, you must ultimately have a classical observer. And I profoundly disagree with that. I think it's not just philosophically wrong, it's even physically wrong. I have an experiment to show that this is a wrong view, in fact. Um, hybrid descriptions of reality never work. As a mathematician, you can understand this very simply because whenever you combine classical equations with quantum equations, they have completely different symmetries. If you want one classical equation to conserve energy, this requires a completely different set of things than if a quantum one conserves energy. And when you put them together, you simply don't know what to do with this entity.
Yeah, it sounds a bit like
It's
Descartes.
incoherent.
It sounds a bit like Descartes' mind-body problem.
That is exactly that's beautifully put. This is a variant. I also think that people who subscribe to Copenhagen also secretly believe that there is something special about consciousness, and I'm not on that side. I'm a strong AI person, but not in the way that people are doing AI now. I don't think current
Yeah.
AI is conscious. I think we're missing something fundamental, but I don't think there is a reason why we can't create an AI.
Well, I believe the same thing, and that's what my research is all about. So I don't want to take everyone's time,
No,
but
it's great. Thank you. It's great.
maybe I can send you something at some point.
Please do.
Well, thank you very much.
Thank you.
Matt, thank you. What a great thread. I saw lots of people nodding. I was nodding furiously myself at times. So, does anybody want to follow that thread with any points or questions, please? Yes, James. James. Yep. James Bryant.
Yeah,
Yep.
can I just ask if I understood you correctly, and I may not have, if to understand quantum information you need a quantum observer, was that correct? Then is there any chance that we will actually understand the information?
Yes, that's excellent question. In fact, that's a beautiful. Indeed, and I think it goes to the heart of why some people still subscribe to a hybrid world, half classical, half quantum. And the reason is that we think of information that we obtain from our measurement as something that must be completely distinguishable. So I must be able to communicate to you one outcome, it's detector one or detector two. It's a zero or it's a one. It must be copyable. I must be able to copy this, communicate to as many people as I like. And it seems that if you allow quantum superpositions everywhere, people would say, well, how do I get any information now? And the interesting thing, the concept called Wigner's friend comes here. What's interesting, in fact, is that quantum mechanics allows classical information to arise within each of these elements of a superposition. So you can have the situation, and that's exactly now I'm starting to describe the one of the experiments in one of my early chapters. You can have an observation in which one observer sees one outcome, another observer sees another outcome. I call them observers just to make this easier. Like I said, I don't believe that they're. It could be one atom gets entangled to one outcome, another atom gets entangled to another outcome. And outside of that, it's all still in a superposition. So this is actually a variant of Schrodinger's cat experiment, where every observer, again, if you like to call them like that, every observer writes down a different state of a physical system. One observer says the photon is in detector 1. The other one says, no, the photon is in detector 2. The third observer outside says, no, 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 it's a superposition of you guys. One sees the photon in detector 1 superposed. All of these are correct in quantum. So quantum mechanics, this is another interesting point, that it has an element of relativity in a very similar way to relativity. You'll be frequently hearing that relativity and quantum mechanics don't go together. But in fact, if quantum mechanics wasn't relative in this way that I'm describing now, relativity would be out of the window. Relativity can only be maintained in quantum mechanics because quantum mechanics is also relative. I don't know if this means anything to you, but I think it's a really interesting it's a really interesting point that I don't think is emphasized enough. Everyone talks about the problem of unifying quantum mechanics and general relativity, but in fact, they have lots of things in common.
So it does, because there's an image which you may or may not be familiar with called a subjective Necker cube.
I love it. I know it. Yeah.
And there are eight identifiable cubes, or 11 identifiable cubes within the cube, but you can only see one at a time.
Yes. Yes.
So there are superpositions, I guess, on that basis, because each observer can see them in different ways, and they fit.
Yes, I think this is
each one.
It's a great classical. Actually, I think I used it in some of my writing. It's a great classical analog, if you like, of what it would mean to be in a superposition. So that's why I also don't like this jargon when people say you make a measurement and quantum state collapses, things collapse. Nothing in quantum mechanics ever collapses. The underpinning elements of reality, these Necker cubes, as you call them, they're called Q numbers, they're matrices, they're quantum numbers. They're always there. You don't collapse a quantum number when you measure it. What you do actually is that your quantum numbers, whatever quantum numbers your brain comprises of, get entangled. That's the language that Schrödinger used, and I think he was ultimately right. They get entangled to the quantum numbers or whatever it is that you're observing. And classical information, interestingly enough, emerges in this way.
Thank you.
It's a beautiful question. Your question is extremely important, and bear in mind that there'll be many physicists disagreeing with what I'm saying as well. So I do want to say it is a controversial topic.
Well, that's a great cue to perhaps bring in Meg, and then I'm going to go to Dave Dewhurst, who's posted a few things. So Meg, would your point around quantum fields and consciousness, please?
Well, as you know, there's lots of speculation that perhaps maybe using the sort of entangled mechanism that you're implying, that this is sort of how we exist in these quantum fields. And so consciousness essentially being information, if you like, or access to information of some kind. That is there a possibility that these properties are found in the field, are part of the field? Yes. Do you think that's unreasonable, or?
No, it's a great question. Actually, you've almost anticipated the end of my book. You always, whenever you have these discussions, there's always a question: what does this mean directly for us and for our perception? Does it have any implications? And I think it does. What I'm not sure. So what I end up suggesting is that by exploring the full range, I think it very much follows on from the previous discussion, is that it seems to me that when we make an observation, this really creates these relative classical worlds, which maybe for an external observer still in an entangled state, but each of us in each branch feels as though there is a definitive outcome. So I end up speculating in my book on introducing some kind of quantum chips into our brain. So the question is whether our brain, I was kind of inspired by Huxley and the doors of perception. Of course, he was advocating taking drugs to broaden your perception. The point that I'm trying to make is that you could make it much more powerful with technology, possibly. And whether actually you could even broaden our perception by exactly right. So could you even explore all of these states in between?
Yes.
So you see, this brings me to this concept. When I talk about this way about quantum mechanics, people say, "Oh, this is many worlds," and yes, it's closest to many worlds, but I think many worlds is not. It doesn't capture fully the exponential set of possibilities. So I think the right language is there is only one universe, but it's quantum mechanical through and through. That would be my way of saying it. And the question is, could we tap fully into that? So I think you're bringing a very important point. The other point I think is quantum mechanics really required even for what we do now? Could it be that some of the mechanisms behind our brain and how it operates. And I think you're right to point out that many people speculate that quantum entanglement could be at play there. And I'm not against, in fact, I think that's possible. What's extremely difficult and what frustrates me as a scientist is that it's hard to think of experiments that could be executed with the current technology. So I'm always talking to neuroscientists and I'm thinking, what kind of signals can you get there? And could we set it up in any way that we could get witnesses of quantum mechanical behavior?
Could I build on that with an example I heard from a physicist who's studying nanomachines that construct base pairs of DNA.
DNA, yeah.
You're familiar with that?
Yes.
It seems and it seems in cells that they survey in instance the entire milieu, and then have a state that comprises an action, a decision point. So this is the number of computations, like 10 billion in 10 milliseconds or something.
Yes.
I mean, this is an extraordinary variety management process to then actually, I hate to use the word collapse, but to decide a state for an action, or an action which is a state decision, if you like. So I find that this is quite interesting. And if you're looking at exploding this at scale, it seems to me you would naturally derive regularities of patterns across such huge systems of possible state machines that are computing in this way. So I don't know. Don't know what you think.
Yes, I think one of the early speculations that I loved. Now I have to remember the name of the person, an Indian physicist, maybe Arvind. I'm not quite sure. The question was, why do we have this replicating machinery like the DNA or RNA as well, which is based on 2 bits, on 4 base pairs? Why 4? Why not 2? We know that you can do everything with Boolean, with binary logic. So how did nature bother to go from 0 to 4? And actually he speculated that this is the first time that you get a double speed up. So if you're searching a quantum database with 4 elements, you can actually find the right outcome exactly as you were describing in a single step. That gives you a huge advantage rather than just randomly looking for the right element to pair with the other one. And I thought completely unexplored. I'm not familiar with any so I can tell you immediately, just very briefly, what the difficulty is. And we do get surprised very frequently that certain mechanisms in biology are seemingly like that. But to a physicist, you would expect lots of quantum effects to disappear simply because these systems are very complex and very noisy. And if the system is not isolated and insulated enough for long enough to perform that operation, then almost all of us would just bet that this would be as bad as classical computation. However, having said this, we have examples from photosynthesis, we have examples from magnetoreception, even I worked on some of these things, where actually we know that some tiny nanomachines, if you like, as you call them, do seem to operate quantum mechanically within the cell. So then maybe it's not a huge jump to ask, what about stretches of the DNA? How long can that be quantum mechanical? Yeah, I think it's a fantastic direction. I actually think this is the future, even of science. Quantum mechanics leaving the microdomain and going into chemistry and biology. This is the next 3-4 decades of science. It's going to define that, actually. Yeah.
Just one comment quickly on the RNA. So you've got microRNA, which tell the RNA how to read the DNA. So you've got this built-in layers. I also think the boundary conditions, what the structures there, where you've got these single photons able to tunnel through, are part of how you constrain, if that's the correct word, and allow for, containing the proliferation that's possible, if you like, in some bounded sense. I'm really, this is not my area, but I think this might be possible, how nature figured out how to, how to do this.
To me, this sounds fascinating.
Yeah.
Actually,
thank you.
Yes, when you say these things, then I think possibly the greatest speculation of all would be that even the origin of life owes it to quantum mechanics and to speed up of this kind. This would be fantastic for a physicist, right? That there is something in biology that depends fundamentally on this. Yes, I like that.
Wow, thanks, Meg. I mean, someone mentioned earlier, I think it was Peter Tuddenham, about the integrative potential for cybernetics and quantum theory, and I think this discussion is really showing it. Which is a great point to bring Dave Dewhurst in, please, who posted 2 questions. Can I ask Dave, for the purposes of time, just for your most popular and pressing question, please?
Okay. I'm not quite sure what I'm talking about, but sometimes when I'm not, I get far more intelligent answers than the actual question. And I feel very queasy in this area. Shannon's information theory is one of a number of information theories. It deals with information averaged over time, so it's not absolutely quantist particular, and it presupposes a space of possibilities, a viewpoint, as it were. And I'm just asking, how far is that analogous to the world, the picture that you're giving us with quantum information theory, Vlatko?
Yes, I think I can answer that. What's interesting is that you have these contexts within quantum mechanics. Again, this goes back to the previous discussion, but maybe I'm rephrasing them. You can choose your classical contexts, which would be like, I'm going to choose what property to measure of my system. So I think Heisenberg has this famous statement, you can look at the world with the X glasses, X meaning the position, or P glasses, P meaning the momentum. But you can't look at the world simultaneously with X. That's the Heisenberg uncertainty principle. So what quantum mechanics allows you is infinitely many, a multitude of ways in which you can extract classical information. But putting these things together is intrinsically quantum. The information is no longer copyable, for instance. So once you have information in position, you've actually completely destroyed the classical information in momentum. And that's where Shannon comes in, because you have to decide, and there is an entity which would be the state of your system, the so-called density matrix, which probably qualifies as the best kind of classical framework. And it's usually the entropy of this that one takes in a way. So that's how you still use Shannon's theory, but you have to combine this multitude of classical contexts into one quantum framework. That's kind of the idea.
Okay, that takes me somewhere. Thank you.
Thanks, Dave. And Peter, just President's prerogative. Final question.
Yeah, I mean, I think we're at the end really, and there was just in a way a question that might prompt responses from cybernetics, and maybe it's something we continue later or kind of later in the bar kind of thing. But does it even make sense to talk of a constructor for reversibility as a kind of theoretical argument? Does that even make sense, Vlatko?
It's a good question. I personally also think that the emphasis, maybe this comes from von Neumann, but it seems to me that the name for this view is wrong. It's a bit like the relativity theory. Relativity theory is exactly about things that are not relative. It's about absolutes. It's about what any observer agrees with any other observer. And it's not space and time. Individually, they are relative. But if you put it together, actually, that's what theory of relativity is about. And I think constructors shouldn't be about constructors, because what you're really trying to do is constructor is almost like an enzyme, I suppose. You want an entity that can facilitate transformations, but in fact remains intact. It remains largely outside of that transformation, so that you can use it over and over again. That's kind of the idea. And maybe it's this property that ultimately leads you to conclude that some things are irreversible, if you like.
Yes. So I think with that we're out of time with respect to your diary, Vlatko. My question was really to prompt a discussion about Ashby and so on and so forth, which we can take offline ourselves.
I'm happy to do that on another occasion, yes.
Yeah, but would be wonderful to hear from you on another occasion. Just to say very quickly, thank you to Peter, Tuddenham and Richard for setting this up. And thank you to you, Professor, for a marvelous education, marvelous contribution. And I will live with it for a long time, and I'm sure many people will. And thank you for really eloquent and bold positions as well. Thank you so much.
Thanks very much.
Thank you.
Thank you very much.
Thank you.
Feel free to leave. I think we will stay to chat.
Thank you. Thanks very much. Thank you.